What up, guys? This is Drew Haynes. I am the SDSUeeTutor. I find that a lot of professors just try to jump through the material and don't actually explain the concepts and try to get you to understand why and what's going on. So I'm going to try to attempt and build an idea of what's going on conceptually in terms of voltages and currents and whatnot. So my email is down here. SDSUeeTutor@gmail.com. I do offer reasonably cheap tutoring around San Diego area, so if you need tutoring, let me know. So first of all, what is electricity? All electricity is negatives or opposites attract. Negatives try to get two positives, right? And I'm sure you've heard that multiple times through physics or whatever, playing with magnets. Opposites attract like charges repel. So all electricity is the flow of electrons. So electricity is negatives trying to get two positives. So and if you look at our little diagram here, you've got a battery filled with positive charges on this side and half of it's filled with negatives over here. If you connect the wire, then all the negatives try to flow up to the positives. And notice this too, because it says current flow is going from positive to negative, right? Current flow is going this way, but our electrons are moving this way. So why is that? This is what's called conventional current flow. This is what we use in classes, and this is what all our equations are based on, positive to negative. Actual electron flow, as we built the model of the atom and figured out what's actually going on, we know that the nucleus has positive charges in it, and then negative charges, or the electrons, are the ones that are floating around it, right? So the electrons are the ones that are moving, not the positives. So later on we found out that negatives go to positives, not positives go to negatives. So that is, note that conventional current flow is different from electron current flow. And we still use conventional current flow just because basically when Ben Franklin was figuring it out, he didn't know what the hell an atom was. So all of the equations got based off of positive to negative, but it doesn't really matter, and all the equations still work out, so just don't question that, just follow it. So the easiest way to explain what's going on conceptually with electricity would be to compare it with water. So electricity and water both have current. Electric current flows from positive to negative, right? In our little diagram, positive, negative. Current flows this way. It is measured in amps, which is just coulombs per second. This is charges passing a point per given second. And if you look at water, water also has current. Water flows from a high elevation to a low elevation, right? So in our little diagram, we've got 5,000 feet at the top of the hill, 0 feet down at the bottom, and current is flowing down the hill. So current's essentially the same. So voltage. Voltage is the same as pressure for water. So voltage is basically just the amount of electrical buildup that you have ready to flow through your conductor. If you look at our diagram here, I really don't know why I drew this. 5 volts. Voltage is measured in volts. So the equivalent would be pressure for water. So pressure is just the amount of buildup that's ready to flow through your pipe. And if we look here, we've got our little gallon jug thing, and the nozzle is keeping it from going down. There's pressure coming down on the nozzle, right? There's a buildup of pressure ready to go. If we open the nozzle, then water would flow through and create a current through the pipe. So another way to talk about voltage is potential difference. You'll start hearing this a lot, and this kind of confuses people. But potential difference is basically just the difference in potential energy between 2 points, and it's not necessarily energy, but just anything really, voltage or anything. It's the difference between 2 points. So if we're looking at it in terms of hills or elevations, you can see that, oh, first of all, everything is relative. Everything is relative. So the potential difference between our 5,000 foot point and ground at 0 feet would be 5,000 feet, right? 5,000 minus 0. Whereas the potential difference between our 5,000 foot point and our 2,000 foot point would only be 3,000 feet, right? There's only a difference of 3,000 feet between them. So the same can be seen electricity. If we look at our circuit, you've got 10 volts here. Our ground is at 0 volts. So if you're saying what's the potential difference across this resistor, you're saying, well, that's the potential, or that's the voltage from this node minus this node. So 10 volts minus 4 volts gives you 6 volts across this resistor. And same thing over here, right? 5,000 minus 2,000 gives you 3,000. 10 minus 4 gives you 6. It's the same idea. So next we move to resistance. And electricity gets slowed down by things in its way. So if we look at our diagram here, we've got 5 volts, and the charges are trying to get through, but there's this big fat resistor right here that's slowing it down. And it's basically just something that's not as good of a conductor as your wire is. So it's not a good conductor, and it's not good at letting charges through. They dope these things very specifically so that you can get whatever kind of resistance you want out of them. But all it's doing is adding extra resistance to the wire so the charges can't move through as fast, right? That kind of makes sense. So if we apply that to water, you can see that water gets slowed down by things in its way. And in our diagram I drew a little beaver dam here slowing down the water. And right, this is not good at letting the water through. It is additional resistance that's not letting the current flow through. And just another side note, the current flowing into the dam is the same as the current flowing out of the dam, right? This isn't going any faster than this is, because this water's slowing down this water, so the current flowing through the resistor is uniform. And same over here. So the charges flowing into the resistor aren't flowing faster than the charges coming out of the resistor, right? Because they're getting slowed down by the guys coming out here. So current is uniform throughout the whole thing. So just keep that in mind. So putting it all together gets us to our magical equation of V equals IR. Ohm's Law. So if you don't remember anything from any videos or anything you read or anything, remember this, because this is ridiculously important. V equals IR. Voltage equals current times resistance, and this is measured in volts, equals amps times ohms. And this is always true. Always, 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 always. No matter what. So I wouldn't be much of a tutor if I didn't go through a couple problems, so I'm just going to do a couple quick examples. We've got a 10 volt battery trying to push electricity through a 2 ohm resistor. So what is I? And this is just simple V equals IR, right? So if we draw our circuit, 10 volts, 2 ohms, 10 equals I times 2. I equals 10 divided by 2 gives us 5 amps flowing through it, right? And that's positive to negative. Current's flowing this way, conventional current flow. So example number 2, V equals IR again, right? V equals IR. We've got a 5 volt battery hooked up to 2 resistors, 2 ohm, 5 ohm, and do note that, don't let this trip you up, there are 5 volts across both of these things, right? From this point, this node, to this node, 5 volts across this guy and this guy. So back to V equals IR. If you're looking through the current flowing through our 2 ohm resistor, we've got 5 equals I1 times 2. I1 equals 5 over 2, gives us 2.5 amps flowing through this guy. And if you look at this guy, the other current flowing through this one, you've got 5 equals I2 times 5. I2 equals 5 over 5, 1 amp flowing through this guy. So, and this can be seen going back to our water analogy as a bucket up here filled with water flowing into a pipe that splits both ways, right? Splits. You go back up here, wire splits. So there are going to be 2 currents that flow through each pipe, and you're saying, well, how much current splits between the two? And it's basically just, it depends on the resistance in each pipe. So right here I wrote sludge resistance, but it could be backup, anything you want, just something slowing down the water going through the pipe. So if there's more resistance in this guy, not as much water is going to want to flow through here, right? If there's less resistance in this guy, the water is going to try and flow faster through this way. So same thing for electric circuits. The more resistance, the less current that's going to want to flow. And these things are both at the same potential difference, so to speak, right? So that's all I have for today. Questions, comments, feedback, any concepts you want me to go over, let me know. I will be coming out with more videos soon. So if you have anything to say, question, comments, or comment section below. Thanks, guys.